Good morning, everybody. Thank you for coming. First of all, let me say how grateful I am to the Simons Institute for hosting this event and this entire program. I'm having a great time here. I'm sure I'm not the only one. And also thanks for the organizer of this workshop too, for the opportunity to speak. I will tell you about functional programming over sets with atoms. This talk is related to some talks that you've already seen at this workshop. On Monday, Mikołaj told you about sets with atoms. And that talk could also be titled Imperative Programming over Sets with Atoms. So I will now do the same routine, essentially, but for functional programming. Yesterday, Joanna, and I'm going to build on the theory that Mikołaj presented. Yesterday, Joanna spoke about first-order definable CSPs, which were essentially CSPs over sets with atoms. And I will also use some examples, very superficially, I will use some examples and some results that she presented. And also Andrzej, on Monday, if I remember correctly, gave a presentation where he didn't mention sets with atoms explicitly, but what he talked about is, I think, a rich source of examples or applications of what I'm going to present today. So this is also related. So this, sorry? Thomas hasn't spoken yet, so this is the past talks. But today afternoon, Thomas will also speak about orbit finite sets. This talk will be a bit unusual for this workshop, in that I will not show you any theoretical results whatsoever. That's because all the theory that I will need has been already covered by Mikołaj and Joanna. Instead, I will give you a rather practical engineering-oriented talk, aiming to show you how that theory could be put to work. Okay, so let's do some programming over sets without atoms first. So let's say we want to do some programming with finite sets. And I'm going to use Haskell syntax because what I'm going to say is a modification of Haskell. So let's say I define, in Haskell, I define a new type constructor set that given any type A constructs a new type set A, which is implemented just as a type of finite list, let's say. Now I've only barely started, but I'm already cheating you. This is not the way at all how sets are implemented in Haskell. It's a lot more complicated than in the actual library. They are implemented by balanced trees for greater efficiency. But let's say I'm going to do this, just for the purpose of illustration.
Also the first line. So what do these brackets mean?
Yeah, oh, absolutely, yes. So you have every right to be lost. So this is just the type of lists of elements of type A. This is a standard Haskell construction. Ordered lists, yes.
So like
sequences of elements. Yes. In Haskell, so they can even be infinite, potentially infinite, but let's forget about that. Let's say I'm only interested in finite sets here. And then I can implement some primitives. For example, I can have a constant empty that returns the empty set. Well, it is probably implemented as the empty list. That's a polymorphic constant in that for every type A there is a constant like that. I can also define some functions like such as insert that takes an argument of type A, an argument of type set A, and returns another set and just inserts the element in the set, adds the element to a set. Then there is a very important function map that given a function from A to B and given a set of elements of A returns the set of elements of type B by applying the function element-wise. And you can define many functions, and in fact in the standard library of Haskell there are plenty of functions of this general kind. They are to a large extent interdefinable, and then of course you may wonder what is the set of primitives that you want to add first, and then perhaps you can implement all the other functions of this kind using just those primitives and not the actual internal representation of, and then the definition of the type constructor set. But yeah, so in the actual library, I think most of them are actually primitives, just because efficiency is very important. And then using these say primitive functions on sets, you can write your own program. So let's say I want to solve the problem of computing a transitive closure of a relation, where a relation is now implemented as an element of the type set of AA, meaning the set of pairs where the first component of each pair is of type A and the second component is of type A as well. So let's say I want to compute a transitive closure. So first I might begin by defining a function of this type. This is a polymorphic function that for each three types A, B, and C computes the composition of two relations. I won't define it here unless you want me to. It is the two-liner. And then using this function, it's a rather boring thing. This is perhaps slightly more interesting. Using now this function that computes the composition of two relations, I can compute transitive closure of a relation which is now of this type, giving an endo relation, say, on type A. I can compute its transitive closure by saying this. So let's say I'm getting a relation R. I first compose it with itself. I get a new temporary relation R1. If this is already a subset of R, it is a subrelation, then I return it. The relation is already a transitive, thank you very much. Otherwise, I add it to R and compute the transitive closure. So that's a recursive function.
Don't you usually start with the identity relation?
Sorry?
Don't you usually start with R1 being the identity?
Yeah, so this is not the transitive and reflexive closure. This is just a transitive closure. If you want to compute the transitive and reflexive closure, this gets slightly different. And then if I say write down a relation of this kind, the transitive closure, well, it returns finiteness. Okay. Other examples of this sort are say graph to colorability. If I have a graph that's a relation, of course, I can write a function that returns the Boolean value, depending on whether the graph is too colorable or not. And that's a very similar program to what I showed you on the last slide. It's essentially a reachability problem. We look for cycles of odd length. If there is such a cycle, then I return false. Otherwise, I return true. Another example is graph 3 colorability, which is a bit different, of course, but then there's a standard procedure of that. We can just, that's a very naive approach to solve 3 colorability. Well, we don't have very smart approaches, but we can just try to generate all partitions of vertices into 3 sets, and for each of them check if it's a legal coloring. So that's obviously an explanation time algorithm, but it's also not very difficult to write down using the primitives that I've showed you. Okay. So this is how programming with finite sets look like, or finite structures. Now let's move to sets with atoms. You've already seen this definition, well, this notion a couple of times during this week. So let's say we have some infinite set of atoms, and you're invited to think of them as natural numbers, but just with equality. And then we can construct sets like these. So this is the set of ordered pairs of distinct atoms, the set of 2-element sets of atoms, and, for example, such a relation. So let's look at this relation. This is a relation, a binary relation on the set of atoms, which is now differently from these two examples. This is defined using 2 parameters, two concrete atoms, 5 and 2. And well, this is the definition. It's definable in the sense explained by Mikołaj on Monday. It's a finite description of an infinite relation, and this is the sort of drawing that explains how this relation looks like. The blue portion is the pairs that are in the relation. And now that we have such a relation, we can, for example, might want to compute its transitive closure. So obviously, this transitive closure exists. In particular, it's this one in this case. And if you if you ask a reasonably skilled programmer to design data types for representing such structures, for such relations, and to write a program that computes a transitive closure, they would probably not have very much difficulty with that. I mean, of course, you can compute transitive closure symbolically, and there is a method for that. And well, I'm sure that people do constraint programming; they do it all the time, and then they may try to write the program that does this. Now, if you ask this skilled programmer to do that, though, the program that they will write will probably be quite different from the program that computes transitive relation for the finite list representation, well, because they will probably work with formulas explicitly. So our goal here is to provide a programming language so that the programmer could write a program for computing transitive closures, for example, writing essentially the same code as for finite sets, working under the intuition of directly manipulating infinite sets, without bothering about symbolic representation by formulas. This is another example that you've seen, well, you saw that yesterday in Joanna's talk. This is we call it the satanic graph, because, well, this is it's an infinite graph, and this is a finite portion of it. It is not three-colorable as you saw yesterday. And you might want to ask whether such a graph given as input is three-colorable or not. And then the question is how to write programs, how to program with these sort of structures. So this is what we do. And we wrote a Haskell library, which is called NLambda, and does exactly that. So what does it do? First of all, it introduces a type atom, which is just elements of this type are just atoms. So natural numbers, but just equality are there. There is also an equality function on that atom. And then it adds, just as on the first slide I showed you, it adds a type constructor set. But now, this type constructor is supposed to implement not finite sets, but definable sets over the type A. Okay. And then I can provide, and this is what is provided in the library, a bunch of primitives that allow the program to operate on these sets. So there is the empty constant. There is a new thing is the constant atoms, which is the set of atoms, and it is an element of a type of set atom. So it's a set of atoms, therefore it's a legal value of this type. Then there is there are these primitives as before, insert map sum. There is also an isEmpty function that is an important primitive. It lets you check if a set is empty. It doesn't return a Boolean value. It returns a new type, which I will explain in a moment. So this formula type is a new type that sort of replaces Boolean type, the Boolean type. It needs to be a bit more complicated than just two-value set. So how do you use this? Let's say you open a session of a Haskell interpreter. If you type atoms, it returns something like this. So this is how the set of atoms is represented. It's a set of A. Well, the set of A for every atom in the set of atoms. So in this output of the library, this capital A represents the set of atoms. Okay. So this is the value of the constant atoms. Let's say I have this. What does this function do? What I'm trying to do here is I want to compute the set of all pairs of atoms. So what it does, well, so let's say this is a function. In the context where an atom A is already fixed, this function for every atom returns the pair of AB. And then if I map this function for atoms, I get the set of pairs where the first component is A. Okay? Then I map it to every A, and this returns some value. This is what the interpreter shows you. This is not exactly what we want. This is not the pairs of atoms. This is not the pairs of all atoms. This is a set of sets of pairs of atoms indexed first by A and then by B. Then what we can do is we can apply the sum function that, given a family of sets, takes the union, and we get what we want. Okay. So this is an actual session of. I didn't do a demo. I recorded the session just to avoid technical glitches. Then I can do things like this. So for example, let's take the set of pairs that we've just calculated. I can now filter this set by a predicate that says that these two atoms are actually equal, and we return something like this. So this all happens in finite time. Also, So let me stress perhaps at this point that if you know Haskell, you may think for a moment that our ability to deal with infinite sets here is nothing new in Haskell because Haskell had infinite lists to begin with. But that's a very, very different data structure that we're dealing with here. So for example, if you take, this set of atoms is very different from, for example, an infinite list that enumerates all atoms. If I now take a membership function that says, so what does this do? This is a function that takes an atom A and checks if A belongs to the set of atoms. It's supposed to return true for every atom. And now I can check that this function actually returns true for every atom. Now if I interpreted the set of atoms as an infinite list, this would loop. This would terminate. But in our implementation, it actually terminates in infinite time. It returns true. So now that I didn't show you on the previous slide what is the actual implementation of the set type constructor, but from these outputs of the interpreter, you can actually sort of figure it out. So let me come back to that slide. So now I can tell you that a set of A, a value of type set A is a list of saying, well, there is some value of type A qualified by a first order formula with some free variables. There's a list of free variables. Var is just the name of a variable. So this is how this works. So how this works is internally in our library, all-bit finite sets are represented by first order formulas and set builder expressions represented as lists with sequences of bound variables and free variables, and first order formulas that qualify the existence of some elements. There is, of course, as you probably may imagine, there are plenty of technicalities that are rather boring, and I'm not going to show you all of them. That's not quite as simple as I make it sound. For example, we must do something with the conditional statement of Haskell, if then else, because it might happen that if we have a conditional statement, if a condition then returns something else, it might be that the condition is a formula on atoms that at this moment doesn't have a determined logical value, because it depends on some atoms, and we don't know whether these atoms are, for example, equal or not. Therefore, we must sort of delay the evaluation of conditional expressions as long as possible. So for example, this is, and for this reason, we had to add to our library as a separate conditional statement, which is now a function called ITE, if then else, which is a replacement for the Haskell standard if then else construction. I mean, Haskell if then else is unfortunately not a function, it is a bunch of keywords, so we couldn't reuse that. So there is a function that says, well, let's say I want this. So in a context where A, B are some atoms where are atom variables and I don't know what they are, I want to evaluate this program. If these guys are equal, then return the singleton of an atom C, otherwise return the set of all atoms. This is well typed because this is a set of atoms and this is a set of atoms, so that's fine. But now what should we? How should we evaluate this? Well, in fact, this evaluates to the following set. It returns the set of the atom C for whenever A equals B, and the set of atoms, well, the atom D for every D such that A is different from B. This is the actual symbolic representation of the value here. As you can see, I did not actually evaluate the condition. I just pushed it back to the value that I did. This is necessary, and for this reason, we had to replace the conditional of Haskell with this, or add another conditional to work with these internal representations. And also, this is the reason why Boolean type had to be replaced by this more complex formula type. But let me stress that for the programmer, it is actually quite transparent. The programmer is invited to think that this is the proper if-then-else construction, and this is an actual Boolean value that is interpreted to some value for every to some Boolean value for every pair of values A and B, and that's it. Yeah? So this is the intuition that programmers should. This is a very convenient intuition. Now, every now and then, of course, our implementation needs to actually evaluate some formula and return true or false, because I mean the programmer might write a program. If this set is empty, write this on the screen. Otherwise, write something else on the screen, and we actually need to do something. So, whenever we want to say that a set is empty, we have a bunch of formulas. We have an internal representation of a set, and we essentially need to check every now and then whether some first order formula over equality is satisfiable or not. So we don't do it ourselves. We invoke an external SMT solver for that. So this entire implementation is integrated with an SMT solver. We used Z3 from Microsoft, but you can use anything. So for example, when you say, well, is the set of atoms empty? Then what the interpreter does is, well, it computes the set of atoms, which is essentially says, well, the set of atoms, you add an atom to the set whenever the formula true holds. Yeah? And then if you check if you want to check if this set is empty, then the library tries to say, okay, so is the formula true satisfiable? And we ask the SMT solver, we ask Z3 for that, and unsurprisingly, Z3 will probably say, yeah, okay, it is satisfiable. Thank you very much. So we return that this is false. You know, so it's not empty. This set. So this is how this works internally. Now, example. Let's say we want to compute transitive closure of relations, but now this is inside the library. So this is the new set constructor, and as you can see, so this is the code for computing transitive closures, and you can see that it is the same code. Well, the only difference is that we now replace this if with our new if then else. That's a minor. It's essentially copy and paste of code. So this is I think rather convenient for the programmer, because it really lets the programmer work under the intuition that these are really infinite sets, and we can check things like whether some infinite set is a subset of another infinite set, or we can compute the unions of two infinite sets, and we know that this will terminate every such primitive. Similarly, for graph 2 colorability, we can also copy the code. There's another example that will be published at Popl, that has been accepted to Popl 2017. The classical Angloid algorithm for automata learning is essentially rewritten. Well, it's not really rewritten. It's copied and pasted with minor changes, and it suddenly becomes an algorithm for learning nominal automata or register automata. So this is actually, I don't know if I find it more exciting or depressing, that you can get Popl papers for free if you use this sort of powerful ideas. So this is a paper with Matteo, who is there, who did a lot of hard work. Because okay, I'm making it so there are technicalities there as well, but essentially this is what happens. It's also essentially the same code.
Just get into the program committee next time.
Now, for the example of three-colorability, there is also the program for finite sets that computes three-colorability, and it starts with generating all three partitions of vertices. Wrong. This doesn't work. Now we hit a problem. This cannot be done because, well, first of all, there are uncountably many of these partitions, so there is no way even to collect them in a reasonable set, let alone enumerate them. So this doesn't work. But still, we can write the program in NLambda for computing, for checking three-colorability, using what Joanna told you about yesterday, using the fact that if a coloring of a definable graph exists, then an equivariant one exists that colors each orbit with respect to monotone bijections of atoms with the same color. So we can generate three partition of orbits, but this seems to be impossible to be written down using the primitives that I've described. In NLambda, there are more primitives that I've hidden from you so far that do things like this. given a list of atoms, a finite list of atoms, and an element of some definable type, does this support the set of atoms? Meaning that does this only use the atoms on this list? Or for example, if you have a set with atoms A, I can define a function that partitions this set into orbits, returns a set of sets and its orbits. So these are primitives that are added to NLambda. They are not difficult to implement using the internal representation, but they don't seem to be possible to be defined from the basic set primitives.
With respect to monotone or with respect to arbitrary automorphisms?
That's a very good question. Thank you. I forgot to mention. So far, this NLambda thing, this NLambda library, is implemented for two kinds of atoms, for equality atoms and for totally ordered atoms. It doesn't matter very much. It matters. So the difference is what kind of formulas you can use to define your sets, and then what is the parameter that you invoke the SMT solver with? What is the theory that you allow the SMT solver to use? So this there is a switch in the library that says use these atoms or use these atoms, and then these functions begin to work rather differently. But it's a parameter of the library, the structure of atoms, in principle. So for this to work, for this line to work in particular, we need to work with ordered atoms. Otherwise, it's not true. I mean, you can still write the program, but it gives you the wrong value, wrong results. Okay, so this is an interesting example, I think, this three-colorability, because we can still solve it, but it's not easy. So I would say that these problems, as far as we understand, fall in three categories: the easy, the hard, and the impossible. So the easy ones are like transitive closure or two-colorability, or the Anglo-Indian algorithm for automata learning, where you essentially copy the same code and it solves from the finite world, and it solves the same problem for the definable world. There are impossible things. Impossible things are those that rely on enumeration of atoms. So for example, there is no way to produce a list of elements of a definable set, and we don't expect it to be possible. There is also the function fold left that is sort of, it really relies upon ordering on elements of a set. It enumerates the elements of a set in some order and then computes some value. This is also impossible, and we fully expect that. And then there's also the hard thing, three-colorability, which is possible, but you need to break the convenient programming. You seem to have to break the convenient programmer's intuition about looping over infinite sets. You need to use orbits and so on. So this is actually, I think we got so carried away with implementing this stuff and with solving numerous engineering problems and trying to achieve efficiency that we sort of neglect the problem of understanding what is hard and what does it even mean to be hard. So I think I don't know if there is any sort of type theoretic perspective on descriptive complexity, essentially, but perhaps there is a connection here that we do not understand at all at this moment, and we would like to. So this is sort of an open problem for the lack of trying, actually. So if you're interested, this is just this is fully ported, fully documented, and according to all Haskell standards, you can download it from there and experiment with it. Ongoing work is this is currently a Haskell library. What we plan to do, and what we're doing now, is integrate it with Haskell more closely by modifying the Haskell compiler, actually, so that you can do away with this pesky ITE, and you can actually work with if-then-else Haskell, and it also make things faster. Also, what Mikołaj told you about is the same thing, but for C++, which will also be published in the POPL. And then, of course, the theoretical problem of understanding the hard crowd, which I think is rather exciting, but I have no idea how to proceed there. But I think it's something interesting might happen. Thank you.
Thanks.
I think we have time for like one or two short questions.
Haskell has this wonderful property of laziness.
Yes,
Do you have a way to deal with non-orbit finite things and like enumerate using laziness the orbits and solve things like reachability where, well, you know that it's reachable. You want to know how. You don't know in the number of steps. I mean,
That's an interesting idea. Thank you. Yes, we haven't thought about it, but there must be some potential. I think the potential is limited, but it's not zero. But yeah, just as, I mean, there's only so much you can calculate with lazy lists, and there's probably transports to this. But by the way, laziness of Haskell is the only reason why this ITE function works, because in an eager language, you cannot have a conditional implemented as a function. That's impossible. In Haskell, it happily happens that you can.
So can you do something like implement ordinal arithmetic? I mean, you can think about, the order type, like an order type of a, ordering on n squared or something like this, or sets of atoms. So like, given to relations of a certain order type, can you compute a relation whose order type is a sum, for example, or the product of this thing?
I'm not sure I understand the question. So are you talking about considering different set of atoms, or computing on the equality atoms with...
No, computing on the equality atoms.
Okay.
So you can think about an ordering as just the order type on a, A cross A or whatever, right? And then so if you have two relations which are linear orders, can you compute a relation which has order type the sum?
Oh, I see.
Or product?
Well, I'd have to think about that.
I will see you immediately. Okay. Oh, real quick.
Okay, no, it's okay.
Okay. Thanks very much.